Hi there and welcome to this talk. I'm Fabrice Parmentier, and in this short presentation I'll be telling you about a study we conducted together with Laura Gallego, an undergraduate student in my lab. And the title of the talk is Deviance Distraction Immune to the Prior Sequential Learning of Stimuli and Responses? This work was supported by the Spanish Ministry for Science and Innovation, as well as the Spanish National Research Agency and the European Regional Development Fund. So let's set the background of this talk with a general observation to do with the equilibrium that exists between two different attentional systems. On the one hand, we have selective attention, which allows us to focus our attention on some stimuli or task at hand while ignoring distractors or task-irrelevant stimuli. And at the same time, we have a separate attentional system that allows us to detect unexpected changes in our environment. And the equilibrium between the two is very important. Having a selective attention that is able to block entirely task-irrelevant stimuli would not be adaptive. Let's imagine, for example, that we are sitting in the library reading a research paper. At that particular time, we might want to focus our attention on what we're doing and not get distracted by anything else around us. So blocking task-irrelevant stimuli at that point might seem advantageous. Yet if the fire alarm goes off, we want to be able to detect that. And that's where the change detection system comes in. So change detection allows us to detect automatically, involuntarily, sudden changes in our environment, things that are not expected. On some occasions, this might be very useful, but there's a cost we pay for this flexibility. Indeed, in many situations, unexpected stimuli might happen that have really no bearing on what we have to do or any of our goals. And in those cases, our change detection system will trigger an orienting response towards those stimuli, which will take our attention away from the task we are currently doing, which will entail a cost or a reduction in performance in that task. Now, this might happen in everyday life situations, whether we are working, cooking, but it may also happen in more safety-critical environments, such as when we are driving a vehicle, or in high workload environments like an operating theater or in the cockpit of an airplane, for example. In the lab, deviance distraction can easily be measured using oddball tasks. One type of oddball task that we've been using in quite a lot of our own studies is the cross-modal oddball task, which we borrowed from a study by Essera et al. In 1998. Now, in this type of paradigm, the participant's task is typically to perform a binary categorization of visually presented stimuli. These are presented sequentially, and participants have to categorize them. So in this case, for example, participants would have to categorize the digits presented on the screen as odd or even. The key characteristic of this task resides in the presentation of task-irrelevant sound before each of the digits. In most of the trials, the same sound is repeated. We'll call that sound the standard sound. On the remaining trials, randomly dispersed across the trials, the standard sound will be replaced by a different sound, either the same different sound every time, in which case we'll be referring to that sound as the deviant sound, or by an entirely new sound every time, in which case we'll be talking about a novel sound. The early studies using this paradigm were primarily interested in the brain's response to the sound, not so much the behavioral response. The task was just merely there to keep participants busy. And in terms of the brain's response to the sound, there's a very clear pattern emerging across many different studies, very robust finding, where if you compare the different waves for deviant and novel sounds, you find that they produced three typical components. About 100 to 150 milliseconds post-onset, you find the N1 and mismatch negativity response, or MMN, which are interpreted as marking the detection of a change or the recomputation of a neural model. And this is followed around 300 milliseconds from the onset by the P3A, which is interpreted as the involuntary orientation of attention towards the unexpected sound. And then in tasks where participants are performing a task, we find a reorientation negativity circa 400 to 600 milliseconds, which is interpreted as the return of attentions towards the primary task, reactivation of task sets, and so on. But my interest really was piqued by the behavioral effect of the deviant sounds. Indeed, when you compare the time it takes participants to categorize those digits, you find that they are significantly slower after a deviant sound than after the standard. And this is despite the fact that the sound says nothing useful about the task. It doesn't tell you what digit is going to come up. It doesn't tell you what response you should produce. This effect is observed in the cross-modal oddball task, but also in other cross-modal oddball tasks, such as tasks where the distractor is tactile and the target visual, as well as in purely visual or purely auditory tasks. So it's a very robust finding. And we're starting to understand some of the mechanisms that underpin this effect.
In the literature, deviant sounds are often described as rare and unexpected. Now, these two things are not the same thing. Take the example of an eclipse of the sun. We can agree that this is a rare event, yet it's perfectly predictable. And when it comes to auditory distraction, we know that deviant sounds cause behavioral distraction not so much because they are rare per se or because their base rate probability is low, but rather because they violate our sensory predictions.
Right, so we know that the predictability of the auditory distractors really matters. It dramatically modulates behavioral distraction by the unexpected sounds. So the next question we asked ourselves was this. So would unexpected sounds still distract me if my cognitive system can predict what stimulus is coming up and can even predict what response I'm going to have to produce before both the target and the distractors are presented? So could we test this? Sure sounds like a good challenge.
Surely you can't be serious.
I am serious. And don't call me Shirley.
So how can we go about measuring the impact of unexpected sounds on predictable behavior? Well, the first step for that is to come up with a task where the participant's behavior will become predictable. So we decided to go with the serial reaction time task. This task was described by Nissen and Bulmer in a seminal paper. And what they found basically is that if you present participants with 4 locations on the screen and ask them to press buttons, corresponding buttons, as stimuli appear in those boxes, what you find is that as you keep repeating the same sequence of locations over and over, their response times becomes faster and faster, which is interpreted as a sign of their learning of the sequence. So we implemented a version of this task in our own study, where we'll first install the learning of a sequence across several blocks of trials, and once the participants have acquired that sequence, we'll then present the standard and novel sounds as task-irrelevant stimuli to measure their impact on performance. So we ran a study in the lab, 52 participants, 12 males, 40 females, undergraduate students in their early 20s, and we had 2 hypotheses. The experimental hypothesis was that stimulus-response uncertainty would modulate deviance distraction, as opposed to our null hypothesis, which would be that deviance distraction is an obligatory phenomenon and will occur no matter what happens in the task. As long as you have a stimulus and a response needed, if a deviant sound comes up, you're going to be distracted. We had a good sample size, 52 compared to the 34 required in order to obtain a power of 0.95 with a type 1 error of 0.05, assuming a medium effect size. So let's have a look at the design. In the first block, participants will perform the task with a sequence of random locations just to warm up. Then after that, from block 2 to block 8, they will be performing the task with a second-order conditional being looped. On block 9, we'll switch away from that sequence and introduce a new second-order conditional that doesn't share any triplets with the first in order to compare their performance for that sequence relative to the learned sequence. On block 10 and 11, we go back to the learned sequence, and at that stage, we should be able to tell whether participants have learned the sequence. After that, we have the auditory distraction phase, where they keep performing the task either with the learned sequence or the unfamiliar sequence, this time in the presence of standard and novel sounds. These sounds are presented at the same time as the location, and the sounds last 150 milliseconds each. Once that phase is completed, we have the third phase, which is a production phase, which we'll use in order to try to get some measurement of how implicit the learning was. So in that phase, we inform participants that there was a sequence repeated in most of the experiment, and we ask them to try to produce as much of that sequence as they can during a block. We then compare the number of triplets that are common to the sequence they produce relative to the practiced sequence. So what do we get? Well, let's start with the findings from the first phase. As you can see on this graph, there's clear speeding of the participants' responses across blocks 2 to 8, where the same second-order conditional sequence is being repeated. On block 9, when we switch to a different second-order conditional that has no triplets in common with the first, we can see that response time shoot back up, which is a good indication that there was learning of the first sequence. And when we switch back to that learned sequence in block 10, we can see that response times go back down, and in fact, learning continues. So let's have a look at what happens when we introduce the auditory distractors. Well, as you can see on this graph, there is a main effect of the sequence. So the learned sequence produces faster response times than the unfamiliar sequence. Nothing surprising there. Not surprising either, the main effect of the deviant sound. Slower responses in the deviant trials relative to the standard. The critical finding, however, here is the lack of interaction between the two factors. So the effect of the deviant sound is the same for the learned and the unfamiliar sequence. Now, of course, a null interaction is a bit of a difficult result to trust. So on top of the frequentist analysis, we also calculated the base factor. We also ran an equivalence test, which showed that the effect is not significantly different from 0 and equivalent to 0. The icing on the cake was to use Bayesian estimation to get credible parameters for our posterior distribution. The 95% high density interval for the difference between the learned and unfamiliar sequence with respect to deviance distraction contained a 0 value, and so did the 95% high density interval for the effect size. So there's good support for the conclusion that deviance distraction occurs whether or not our responses are predictable. Finally, let's have a look at the results from the production task, where we compared the number of triplets that were common to the learned sequence and the sequence of responses produced by participants once they were informed that there was a sequence being repeated in the experiment. And here we found that the proportion of triplets in common was equivalent to chance. All right, let's keep it short in just 3 points. Point 1, deviance distraction affects behavior irrespective of our action's predictability. Even when the cognitive system plans the response ahead of the presentation of the stimulus and the distractor, unexpected sounds do impact behavior. In that sense, and that's point 2, deviance distraction does appear to be an obligatory phenomenon. It also shows that the unexpected sounds don't really disturb the processing of the targets per se, but rather it fits with the view that's been proposed recently that unexpected sounds trigger a transient general inhibition of the motor system. So in this sense, it looks as if unexpected sounds will disrupt any ongoing action. And so it fits with the general idea that our attentional capture system will be on alert for any unexpected sounds and interrupt whatever we're doing in the service of going and explore what that new stimulus might be and whether a new course of action may need to be taken. You can find more information about our study in our paper. Thank you very much for your virtual attendance and your real attention. In the literature, deviant sounds are often described as rare and unexpected.
That these two things are not the same thing. And when it comes to auditory distraction, we know that deviant sounds cause behavioral distraction not so much because they are rare per se.
So the next question we asked, the question we're asking in this presentation, one question we asked ourselves next was this: